Yeah, hello everyone. Welcome to the NPTEL course, Functional Analysis. We are in the week 8 of a 12-week course, and in this session, I'm going to explain some of the problems in the assignment sheet so that will help you solve other problems by your own. Okay, so let's get started. So question number one says, which of the following statements are true? The space CC over R is included in L1 over R, and the inclusion is continuous. Okay. When we consider CC over R, we have to take the supremum norm. Okay. Let's see if the inclusion is continuous. Okay. First of all, it's included that you can see because CC over R is just a space of all continuous functions with compact support. That means after some compact set, yeah, whatever may be the function in the set, after that it's going to be zero everywhere. Like so, yeah, something like this. Yeah. This compact support. So you can just integrate the function. If you just integrate the function over R, it is just the integral in this AB, and since it is continuous on this AB, it's integrable. So this always the inclusion will always be true. CC over R is contained in L1 over R. Yeah. But the question is, if you consider CC over R with infinity norm, then the inclusion is continuous or not? Whether L1 is with his L1 norm. Okay. Let's see. Consider the mapping I, if I call it, from CC over R to L1 over R. Is that I of any element F is just the same element F. So when we say F is continuous, that means if suppose this I is continuous, then there exists some C such that norm of F, now one norm is less equal some C times norm of F infinity norm for all F belongs to CC over R. This is just the definition of linear continuity. So now what we'll do is, my claim is this is not true. The inclusion is not continuous. How will we do? We'll just create some sequence of functions, fn's. Okay, so fn's are like you take minus m n, and in that interval, this is 1 by n, this length, and then you just decrease it slowly to 0, maybe to 1 plus 1 minus n minus 1, then it's 0. Yeah. So you have the fn's has a compact support, like minus of n plus 1 to n plus 1 it's non-zero, otherwise it's 0 everywhere. That means this fn's belongs to CC over R for all n belongs to natural numbers. And what we can see is norm fn infinity is what? 1 by n. Yeah, because this is the height, you can see the height, which goes to 0 as n goes to infinity. Yeah. But if we calculate norm fn one norm, which is just integral this is greater or equal the integral in this region. Yeah, which is what you can just say this is a rectangle just so with the base of 2n, height of 1 by n, which is 2. So one norm is greater or equal to always, but the infinite norm goes to 0. So if we just see this inequality here, if you get such a say, then what will happen is 2 less equal norm f fn's one norm, which is uh, less equal c times norm fn infinity, which is c times n, c by n. Yeah. So, but this is not, this should happen for all n belongs to natural number, which is a contradiction. Where this guy here goes to zero and then goes to infinity. So this is not true. Hence, the inclusion is not a continuous line. Okay. So this is wrong. And the second one. Second one says the C01, the set of all continuous functions on 01 is included in LP01 for every p going from 1 to infinity, and the inclusion is also continuous. So this is true. Okay, so we have to check. 2, not 2, it's B. So first of all, if you just take C01 with infinity norm, then the norm is same. I mean, if this is contained in L infinity 01. Yeah? And also the norm is same because here the essential supremum when taken on the continuous functions of 01, it is just the supremum. So there is nothing to check here. It's always true. And since it is the exact same, it's continuous. There is the because the norms are same, hence it is the inclusion is continuous. There is no need to check. Okay, we have to just check for LP for LP with yeah. Okay, so okay, what is norm? I mean, if you just take a function f from C01, it's continuous since it's integrable. That's no need to check about that. It's straightforward. So it naturally belongs to LP. We just have to check whether the inclusion is continuous or not. So if f belongs to C01, you just calculate norm fp. Okay. So yeah. So this is integral from 0 to 1 modulus of f raised to p whole raised to 1 by p. Yeah. But because f is in C01, we have it's a supremum. It's a bounded function, right? Continuous function on compact set. The image is again compact. So we can just take the supremum out and this will just remain 0 to 1 1, which is just nothing. Hence the inclusion is continuous because you can straight away see if I just include C01 into LP01, then from this inequality you can just see that the needed C is 1. Yeah, so that the I of any element F norm is P norm is less equal F infinity norm. So the inclusion is straight away continuous. I need to check. Okay. Now we'll go to the so the second one is false. Sorry, the second one is true. The inclusion continues for every p. The third one, the space L201 is included in L10 infinity. Sorry, L20 infinity is included in L10 infinity, and the inclusion is continuous. So in fact, in this question, we even don't have to check about the continuity. The inclusion is itself not true. L2 is not included in L1. Paper is finished. Okay. So what part C asks is whether L201 is contained in L101. The answer is no. Example. So we have to give an example of L2 function which is not an L1 function. Okay. Okay. So let's define f as like this. Okay. No, sorry. 0 to infinity you want. So for each natural number 1, 2, 3, 4, go on. Oh, 0 to 1 you define the value as 1. Then 1 to 2 you define the value as half. Then 2 to 3 you define the value as 1/3. Okay. Like this you go on. Yeah. So that means f is defined at fx equals to 1 by n if x belongs to the interval uh, okay, how to write this? Hmm. N minus 1 to n. Yeah, you can write like this. Hmm. So like for n equals to, like for all n belongs to natural number. If you take n from n equals to 1, then 0 to 1. If x belongs to 0 to 1, value will be 1. Yeah. If x is in 1 to 2, so n equals to 2 here, then the value will be 1 by 2. Yeah, that's correct. This is the function. So this function, you can see it is integrable, the L2 integrable. And what, I mean, we can just calculate what is the uh, mod f2, or first let's first calculate just mod f, 0 to infinity. So you can just say, you can just integrate it piecewise, and for each integral, in for each piece, the integral is just the area of this rectangle. Yeah. So this will be summation of integrals of all these pieces, and all these pieces, the integral is what? The length is 1. Sorry, the what do you say? The base is 1 and the height is 1 by n. So just 1 by n. So, but this is not finite. This goes to infinity, as we know. Isn't goes to infinity. I mean, this summation is not finite. Yeah. Hence, f doesn't belongs to L1. But what is 2 integral? This is summation now. Same. The values will be 1 by n square simply. And this is finite, as we know. Yeah. Hence, f belongs to L2. There exists an L2 function which is not an L1 function. So L2 is not contained in L1. Yeah. Okay. So the option C is wrong. Yeah. Okay. So now we'll go to question number 2. Okay. The strangely defined domain. So how there is an operator A, and you have a specific domain of the operator given by a set of all L2 functions for which there exists a G such that this hold integral f phi dash equals to minus of integral G phi. This should happen for every phi in D, script D, where there is a special description of the script D given that the script D is a dense subset of L201. Okay, so we have to check whether A is densely defined or what. Okay, let's see if I mean let's just say how what is this domain. I mean, can we somehow identify at least some subset of this domain or something, so that if we can obtain a subset of the domain which is dense in L201, then we can say that A is densely defined, right? What I want to say is it is enough to show that there exists some what do I call, suppose S subset of domain of A such that S is dense in 201. Yeah. Then what can we say? Then A is densely defined, because then domain will be dense, right? Okay. So what the immediate dense subset of L201 we can think of is C dash 01, because anyway differentials are involved here. And this is going to be just a differential operator, as you will see. So if you just take f belongs to C dash 01, okay. So and just calculate for any f, for any phi, sorry, belongs to script D, yeah, that you can calculate integral 0 to 1 f phi dash by the what do you say, the multiplication rule of integration by parts, you will get here as f times integral of phi dash, which is phi. So f phi from 0 to 1 minus integral of integration of, so derivative of f integration of phi dash, which is again phi. This is what you get. But then this value will be what, f at 1 phi of 1 minus f at 0 phi of 0. Yeah. So but this phi belongs to D, which is subset of L201, right? So the convention is, because L2s are functions which are integrable, right? LP integrable with the Lebesgue nature. So the integrals of any two functions, if we change on some major zero set, the integral will be is going to be the same. So we just, with the convention, we assume that for every phi we can just assume the values are at 0 and 1 can be 0. Yeah. So like the values at 0 and 1 does not make any change. So we can just assume this is 0, this is 0. So ultimately what we get is integral 0 to 1 f phi dash is equals to minus integral f dash phi. So from the definition of the domain of A, what you get is f belongs to uh, domain of A, and AF equals to f dash. This is the G in the definition. That means C dash 0 1 is contained in domain of A. Cool. And what is for every f belongs to C dash 0 1? What do you have? AF equals to f dash. This is just the differential operators on set of all one-time continuous functions. Yeah. And anyway, this guy here is dense in L201. Hence, A is densely defined because its domain is dense. So question number 1 is true. Okay. So next is A is bounded. Yeah. So we can see it's a differential operator, and it's a universal property that the differential operator is not bounded, because we can just check it with the polynomial functions. Okay, I'll just give the example here. B. Okay, the first one, yeah, first one densely defined. Now we have to show whether A is bounded or not. Okay, so let's define fn's as fn of t equals to t power n, simply the polynomial functions. Now, by the A option, what we have is this fn's belongs to domain of A because they are integrable functions. They are in C dash 0, correct? And so now what is norm fn? This is integral 0 to 1 t raised to 2n dt, right? So which is 1 by 2n plus 1 simply. Yeah. And what is the norm of AFN squared? Integral 0 to 1. This is n times t raised to n, right? Squared. So this will be n square upon 2n plus 1. Oh, wait. This is n minus 1, right? Yeah. Then this will be n square 2n minus 1. 2n minus 2 plus 1, 2n minus 1. Yeah. So, but you can see now what we need is, if A is bounded, then there should exist a constant C such that norm of AF should be less equal C times norm of F for all F belongs to domain of A. But from this here star, our norm of Fn goes to 0, but norm of AFN goes to infinity. Yeah, so this norm AFN cannot be bounded by some constant here. Yeah, so this is not true. Since A is not a bounded function. Okay, so this is wrong. Okay, then we have to check whether A is a closed operator or not. Okay, if I just recall the definition of a closed operator, when do we say, suppose A is an, okay, not A, I'll just take T. T is an operator from x naught to y, yeah? X naught is subspace of X, is closed when we say if you take any xn in x naught, okay, sequence, such that xn converges to x and txn converges to y, then we have x belongs to x naught and tx is y. This should happen, yeah, for a closed operator. This is the definition of closed operator. So here our A is defined from domain of A, which is a subset of L201 to again L201. Correct. Yeah. Now we want to check whether A is a closed operator or not. So if we just take a sequence, suppose Fn's contained in domain of A, such that Fn converges to F, yeah, in L2, and AFN converges to suppose G again in L2. So okay, so Fn converges to F in L2 and AFN converges to G in L2. Yeah. So what we have is Fn belongs to domain of A, right? Fn belongs to domain of A for all F. Sorry, for all N. That means integral 0 to 1 Fn phi dash is equals to integral 0 to 1 minus of AFN into phi. Yeah. So now if you apply the dominated convergence theorem here, because Fn goes to F, right, pointwise, we can just apply dominated convergence theorem and we'll just directly get this guy here. So by the definition of domain of A, again F belongs to domain of A and AF equals to J. This is just a straightforward application of dominated convergence theorem. There is nothing in detail here. You can just look for it again. Okay, so this question number 2 was done. Here is a closed operator. You can just relate this operator for just c dash 01 to c01. I mean, it's not the same, but you can just relate for the intuition. Yeah, here also the operator A is not bounded. Same, you take the polynomial functions with norm infinity also. For polynomial functions if you take t raised to n, suppose their norm infinity is 1, but norm of a t n, I mean as a function, uh, is equals to n. So it maps a bounded set to unbounded set, the infinity norm. So it's not bounded there also, but it is closed there because of a result in function analysis. Like if we take sequence of differential function which converges to an f, okay, I mean if fn converges to f and fn dash converges to g, then we know that f also belongs to c dash 01 and f dash is g. Yeah, this is a theorem, a well-known theorem in Rudin. So this is kind of generalization of this kind of differential operator to L2 spaces. So you can just relate the same things there. Okay. Okay, so we'll go to question number 3. Okay, so okay, domain of A and A operator as above. Okay, which of the following statements are true? Okay. C dash 01 is contained in domain of A. Yeah, that we just shown. Yeah. If A is true, then for every F belongs to C dash 01, we have AF equals to F dash. Definitely, we just now shown it. If A is true, then every F belongs to C dash 01, we have AF equals to minus F dash. No, we got F dash, right? Yeah, we have dash. No, this is not true. Wait, what we had? Okay, what was the question? Okay, for this f, there should be some g here. Yeah, so when we looked, integral f phi dash is coming minus of integral f dash. Yeah, so af equals to f dash, right? Yeah, that's correct. Yeah, so this is false. Yeah. F equal to f dash we got, so this is false. Yeah. Yeah, so there was okay, there was nothing in this question. Okay. Already explained everything in the question number two. Okay, so we'll go to question number fourth now. Just a minute. Yeah, sorry for that. I had to take a call. Okay, so we are on question number fourth now. So okay, as it is, it's defined, and for the domain we are defining norm f h to be norm f2 plus norm g2 now. Okay, so the following statements are true. H is a Banach space. Oh, okay. Mhm. So okay, we'll just take the any Cauchy sequence, be Cauchy sequence in H. Yeah, and okay, we know that anyway this H is subset of L201 and L201 is complete. Yeah. So okay, we'll just see if we can do something in that. Mm, okay. So if we just take Fn minus Fm two norm, then that is less equal Fn minus Fm H norm, yeah, because we are just adding some another non-negative term. And this is less than epsilon for all n comma m greater or equal capital N. There exists some capital N. Yeah. Yeah, that means the sequence Fn and similarly the sequence Gn also are Cauchy in L2. And L2 is complete, which implies there exists some f comma g belongs to L2 such that norm of Fn minus f2 goes to 0 and norm of Fn minus g2 sorry gn minus g2 goes to 0. So the claim is that Fn minus f h norm goes to 0. Let's see. Okay. Okay. Yeah, and yeah, one thing also we needed, that is it true that f dash is equals to g? Yeah, that also we want, right? Yeah, but that follows from the Rudin's theorem, like differentiable functions goes to g, then the g that the the limit point is again differentiable and it goes to g. Yeah, so we have this thing. So what is norm of Fn minus f h norm, which is norm of Fn minus f 2 norm plus norm of Gn minus G2 now, and we know both these two goes to 0, so this goes to 0, and Fn goes to Fn h, which implies every Cauchy sequence is convergent, which implies script h is Hilbert's sorry, Banach's. Yeah, okay. Also, you can give another reasoning that this is the graph norm. Like, I mean, this is the usual graph norm we define for any closed operator. So every any operator, and if the operator is closed, then the graph norm is a complete norm. Yeah. So another reasoning is graph norm is complete. Operator is closed. Yeah. So it follows from that also. Yeah. Then we have to say part B. Yeah. So the part one is true. The part B says the inclusion of H in L2 is continuous. Ah, okay. Yeah, this follows because if you just include it, what will be like if suppose I is H2 L201, such that I of F equals to F, then what is norm of IF is norm F2 norm, but which is less equal norm F2 norm plus norm G2 norm because just non-negative, and this is H norm, which implies I is continuous. Okay. Okay. Now I guess B is done. The inclusion of H in L201 is continuous. Okay. The third one now, if H is a closed subspace of L201. Yeah, because the operator is continuous. As the operator is closed, we have proved, right? So yeah, this follows. You can just verify this thing. We have proved, in fact, for proving the operator is closed, that this is closed. Okay. Fourth is done. Next is yeah, okay. Question number 6. Okay, fifth is I guess similar thing. You can just do it. I'll just explain the sixth one now. Okay, there exists G in L101. Which of the following statements are true? We have to check basically. And it's saying there exists G in L1 such that integral 0 to 1 G phi dx equals to phi of half for every phi belongs to D. Oh, that's a big statement. Okay, so for this we have to use a statement given in the assignment sheets at the top that what we have given is if you take K a compact subset, then there exists a phi belongs to script D such that 0 is less equal phi less equal 1 and phi of uh, K is 1, they kind of. Yeah, okay. Actually, the we can also say that the support of phi is again in K, but okay. Okay, what we'll do here is uh, we'll take the kns to be close interval maybe half minus 1 by n to half plus 1 by n. Okay, like for n maybe greater equal some large, some 2 suppose. Yeah, for n greater equal to this starts from 0, 1. Yeah, so yeah, we are in the set. Yeah, so for but what we have is the point half will always belongs to Kn for all n belongs to natural number. This is what we need. And now for each of Kn, because it's a compact set, there exists some phi n's, okay, belongs to D such that the whole thing works. Like phi n is constant 1 on Kn, and the support of phi n also is contained in the Kn. Yeah. So when after Kn, the whole thing is 0. So now if we just integrate 0 to 1, if suppose there exists some G, there exists some G, whatever in L201, right? We wanted L1, L1. Hmm. Such that integral 0 to 1 G phi dash, yeah, G phi dash, sorry, G phi equals to phi of half. Then you just calculate what is integral 0 to 1 G phi n, because what we know is here phi n of half is always 1, yeah, because half always belongs to this set. What is integral 0 to 1 G phi n? This is integral on Kn G, right? Because phi n is 1 there. And I mean, what is Kn? It just goes from half minus 1 by n to half plus 1 by n G. But you can see as n goes to infinity, these points are just going both to 1 by 2. So this has to go to 0. But this is not. This is phi n of half is always 1. So this should not happen. What we are getting is 1 at left hand, at right hand side we have 1 and this guy is going to 0. So this is not true. Yeah. So there cannot exist a G in L1. This is wrong. Okay. Let's look at question number B. There exists a G belongs to L201 such that integral G phi is this guy. Okay. Okay, maybe we just if we just integrate this thing. Okay, let's okay, so let's see if we take sine pi x phi dash, and this integral will be by using partial integration by parts. Okay, what we'll get is this into integral of phi, which is phi 1 minus phi 0, which is again 0, then minus of integral of derivative of this, which is pi cos pi x, then integration of phi dash is phi. Yeah, okay. This is integral minus pi cos pi x times phi. So is this what we wanted? I mean, if you just take g to be minus pi cos pi x, then integral of g phi is equals to integral of this is yeah integral of sine pi x phi dash. Yeah, yeah, that's true. This works. Yeah, so there exists a g. This is true. Okay, this guy is true. Now the C option. Okay. So let's see. In if you just integrate this guy in 0 to half phi dash minus half to 1 phi dash again. So by just fundamental theorem calculus, this is just phi of half minus phi of 0, again minus phi of 1 plus phi of half. So without loss, this can be assumed as 0. I mean, as I said, the convention is we can assume. It's just 2 times phi of half. But again, this is equal to, I mean, if there exists a g, then this should be equal to integral g phi 0 to 1. So this is similar to, again, by 1. This is not possible. We have shown in part 1, part A, in fact, that this is not possible. Because this is nothing but this g of half time multiples, a constant multiple. But what we are getting there is a sequence phi n for which this was going to 0. So this also cannot happen. Yeah, so part C is also false. Yeah, so only thing true here is part D. Okay. Maybe I'm going a little fast in here, but if you just maybe if watch it again or see it by yourself, it's clear. It will be clear. Okay. Let's see question number 8. Okay. Okay. So what question number 8 saying is that f belongs to CC 0 infinity That's rest of all continuous functions with compact support with domain 0 infinity. They are defining operator t as tf. Now tf is again a function. Tf of x equals to 1 by x integral 0 to x ft dt for any x positive. Okay, same thing. Okay. Which of the following statements are true? Function tf is bounded. Okay, let's just see if we can explicitly see what functions tf is. Yeah. So see, for each f, there exists a and b belongs to R, which is compact support basically, such that fx equals to 0 for all which doesn't belongs to AB. Or I can say x belongs to open 0 infinity minus AB. And because this AB has to be compact, A has to be positive. Okay. So what is TF? 1 by x integral 0 to x f t dt, right? This is how it defined. Yeah, correct. So if we see like in three parts, if x is belongs to 0 to A, yeah, what we have, fx is anyway 0, that means tf at x is again 0, no problem. And if x belongs to AB, this means tf of x equals to, okay, yeah, but this is just an integral from A to B, not A to B, A to x ft dt. And this is well defined. This is well defined, no issues. And if x is, I mean, belongs to B to infinity, yeah, then what do you have? Tf at x will be equals to 1 by x integral, it will be 0 to a, it's anyway 0, then A to B. Then after B, it's again 0. So again ft dt. Yeah. So if you call this integral as some c value, then this is just c by x. Okay. Perfect. Yeah. So this is the explicit representation of the function tf for every f. Yeah. Or I can call this as cf. I mean, this depends on f. It's constant value. This is anyway constant, but it's depending on c. Okay. Now what? The function tf is bounded. Okay, is this true? Where the both norms are the infinity norm. That's understood. Okay. So what we are getting is, if you divide the 0 infinity as 0 to a, then a to b, then b to infinity. Then on this part function is 0, this part function is bounded because it's continuous, defined on compact set, it's bounded. And on this part function is, again, function is what? It's not 0, function is this guy, c by x. And if x is greater than b, cf by x is less equal cf by b. Yeah, so again bounded. So on every part the function is bounded, and so it's done. Yeah, tf is bounded. Okay, which of the following statements are tf is bounded? Okay, that's fine. Now tf of x goes to 0 as x goes to 0 and as x goes to infinity. Okay, this is nice. So tf of x, again if I write it here, it's 0 and x belongs to open 0 to a, then the value, I mean, whatever it is, the fixed value, not fixed value, but okay, I'll just write integral from mm, okay, a to x, I can write ft dt if x belongs to ab, and it is just cf by x if x belongs to b to infinity. This is what our tf is for every f belongs to cc or r, cc or 0 infinity. Okay. So if fn, I mean, okay, sorry. If x goes to 0, yeah, then we are in this interval. Yeah, I mean, after some point it's going to be less than e, right? If it's going to be 0, then. So in this interval, anyway, this its value is 0. So yeah, no problem. So TF also goes to 0. TF of x. And this is what we wanted, right? If x goes to 0, we got TF goes to 0, no problem. And if x goes to infinity, then at some point it's going to be greater than b. And when it's greater than b, the value is CF by x, right? X going to infinity, which implies x is greater than b, which implies f of x equals to a constant upon x. And if x goes to infinity, this goes to 0. So if x goes to infinity, yes, so this option is correct. Okay. Now what we have, TF belongs to LP 0 infinity for every P belongs to 1 to infinity. Yeah, less equal. Okay, so this is wrong because what we can see in the representation, CF when it goes from B to infinity, it's this guy. Yeah, and we know that the 1 by x doesn't belongs to L1. So this cannot belongs to L1. But from the same representation you can see simply because it's bounded in this guy, and here it is CF by x which belongs to LP for every P greater than 1, also in infinity because it's bounded, and here it's 0. So TF belongs to LP for all 1 strictly less than P less equal to infinity. Okay, yeah, that's good. Hmm. So now we have the option C as correct. TF belongs to LP. Hmm. Let's see for question number 9 now. Okay, F belongs to CC0 infinity the same. TF defined as above. Okay, exactly. Which of the following statements are true? TF is differentiable in open 0 infinity. Oh, yeah, because you can see in parts. Yeah, like TF came as just 0, then the function 1 by x integral a to x ft dt by fundamental theorem of calculus. This guy is differentiable here. This is just constant 0. This is CF back. So this is also differentiable because x is greater than b. Yeah, so each part is differentiable and it's continuous and at the endpoint since yeah, TF is differentiable in 0 to infinity. Just easy to follow. Then for every x belongs to open 0 infinity, we have fx equals to tfx plus x tf dash at x. Okay, let's see. Okay. Hmm. Okay, what we know is tf at x equals to 1 by x integral 0 to x ft dt, right? It means integral 0 to x ft dt equals to x tf at x. If you differentiate on both sides, that means here you will just get fx, okay, which is equals to derivative of this, which is x times tf dash at x plus tf at x. Derivative of x is 1. Yeah, this is what we get fx. So is this what we wanted? Fx equals to tf at x plus x tf dash at x. Tf at x, yeah, it's fine. We got this. Now we have to show whether norm tf2 is less equal to 2 times norm f2. Hmm. Okay. Okay, so we have this equation. How about we just multiply this equation by TF again? So TF at x into fx equal to x into TF at x into TF dash at x plus TF at x squared. And now if you integrate, yeah, so Here we have integral 0 to infinity tfx plus x equals to this guy here. Okay, we can write here as x times this is derivative of tf at x, right? Because then tfx into tf dash at x, yeah, yeah, we can write like this. Tf at x squared, I guess, yeah. 2 times tf of x, yeah, and then half maybe outside, yeah. 2 times tf of x and tf dash at x, yeah, that's correct. You can write it like this. Okay, then already we had dx here, uh, plus here this is integral mod tf squared. I mean, this is just norm of tf squared, yeah. Okay, and this here after integrating x, this is minus half times because it's x squared by 2 and then integral with respect to tf. So this is half times again integral modulus of tf at x squared because by substitution again x, and this is norm tf squared. So this is also again norm tf squared and minus, okay, so this is half times norm tf 2 squared, yeah. So what we got here is half times norm tf 2 squared is equals to integral 0 to 1 tf at x into fx dx, but by the Schwarz inequality, this guy here is less equal norm tf, yeah, uh, yeah, norm tfx, sorry, norm tf uh, into norm of f. Okay, so what we have is norm tf squared is less equal 2 times norm 2 tf into norm f. But yeah, this squared gets cancelled with here. So we have norm of tf is less equal norm of, yeah, just some rough calculations. Okay, this everywhere it's 2 now, 2 now, 2 now. 2 now. That's it. Hmm. Okay, so here ninth C option is also correct. Okay. Yeah, so that's it. This is the week 8 assignment discussions, and I have discussed some, I guess, 7 or 8 problems there. You're just left with some two, I guess, 2 or 3 problems. So I hope you understand the solutions, how to deal with this LP spaces and all. Okay, so we'll see in the next assignment discussion. Okay.